This video 1.6, calculating limits using limit laws. I'm not going to spend of your pre-class assignment is to read the section from the textbook and to write these laws down. So be sure that you've completed that yellow reading quiz and written these different limit laws down. In fact, you may find it helpful to stop the video and do the reading first, and then use to guide you as you're watching this video. Here are the first 5 limits. State these laws in words, which it's a good practice to be able to take a mathematical statement and put it in words. So we could see that from number 1, we could interpret this to say that the limit of a sum is the sum of the limits. So the limit of 2 sums as x approaches a is equivalent to the sum of the 2 limits. And with the limit law number 2, the limit of a difference is equivalent to the difference of the 2 limits. And limit laws 3, 4, and 5 are simply multiplying the product of 2 limits and looking at the quotient of 2 limits. We see that the limit of a constant multiplied by the function is equivalent to the constant multiplied by the limit of the function. The limit of a product is equivalent to the product of the limit of a quotient is equivalent to the quotient of the limits. You'll be able to practice those limit laws when you do the practice problems, the homework. If we look at the product law, we could move on to number 6, and using the product law, we could derive the power law. So, for example, if we did the limit of f of x times f of x, we could use the product law to say that this is the product of the 2 limits, like this. The limit as x approaches a of a product functions is equivalent to the product of those 2 limits. And so we could rewrite this as the limit as x approaches a of f of x squared. So we can transfer this over to see that this is the limit squared. And so on, we could do this by inserting in a third f of x, and this would be cubed, or a fourth f of x to the 4th, and so on. So we can derive the power law using the product law. That's law 6. And then law 7 and 8, the limit of a constant, regardless of what x is approaching, the limit of a constant is always simply that constant. So let me show you an example of that, because sometimes when something is so easy, it'll seem like I must be missing something. So let me show you. Pick a constant and pick any value approaching 101. The limit of 7 as x approaches 1 is just 7. The limit of negative 43.2 divided by 9.7 as x approaches anything, negative 3. is equal to that constant by 9.7, and so on. So the limit of any constant is equivalent. Here's a really important one to become accustomed to. Pi. The limit of pi. Remembering that pi is just a special constant. Let's let x approach anything. As x is getting closer and closer to 9, the limit of pi is just pi, because pi is a constant. So those are some examples of the limit law number 7. Let's look at limit law 8. The limit of x as x approaches a is equal to a. So let's say the limit as x approaches 5 of x. The limit of x as x approaches 5, as x is getting closer and closer to the limit of x is equal to 5 itself. The limit of -4 is equal to -4, and so on. So the limit of x, if we have it written just like this, the limit of x as approaching some value a is going to be equivalent to a itself. Let's look at the 9th and 10th power rules. The limit as x approaches a of x to the n, we could follow the same procedure we used in looking at the limit laws 6, 7, and 8, or if you applied your knowledge of rational exponent. So if we have x to the 1/3, remember that that's the same as the cube root of x. So a rational exponent, an exponent like 1/3, a third root of x. So 9 and 10 go hand in hand, and then also with 11. Let's look at something new that's a property, not a limit law, but a property. And this direct is going to come in very handy when you're evaluating limits. If f is a polynomial or rational function, and a is in the domain of that function, then the limit of f of x as x approaches a is equal to f of, I'll show you what that looks like. If we have the limit as x approaches, let's pick 5. And then let's use some polynomial just to start nice and easy. Let's say x plus 7. The limit of x plus 7 as x is approaching 5 is going to be equivalent to f of 5. So in other words, we go to our x plus 7 and we replace the x with 5. So the limit of x plus approaching 5 is equivalent to 7 plus 5, or 12. That's direct substitution. You can often evaluate a limit with the direct substitution property. So again, we're going to replace every x with 2. Direct substitution. Substitute x in with a 2. So we'd have 2 squared is 4, 3 times 2 is 6, plus 1 gives us a result of 11. That's the direct substitution property. We'll use that number of times when we're evaluating limits. And Functions with the direct substitution property are called continuous at a. So in general, we have the following very useful fact. If f of x is equivalent to g of x, when x is not equal to a, limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, provided that that limit exists. So if the limit of f of x as x approaches a and the limit of g of x as x approaches a, if those are, and if f of x equals g of x, then the limit of f of x is equivalent to the limit of g of x. That's an important, useful fact that we'll see pop up. Finally, and this is a very important property that you're going to see come up. It'll certainly be on a test, on a final. This is an important concept to understand for a limit, that a limit only exists if the limit from the left and the limit from the right. So here's an example of a limit that doesn't exist. As x is approaching, let's call this 2. As x is approaching 2 from the left, we could say that the limit is 1, because from the left, as x is from the left, the value of the function is approaching 1. Look at from the right, let's say the function does something like this. So the limit as x is approaching 2 from the right, coming in from the right, notice that the value of the function is approaching 3. Sorry, let me put in that f of x there. So the limit of f of x as x approaches 2 from the right is equal to 3. 1 and 3 are not equivalent. We're getting two different limits. So we can say that the limit as x approaches 2 of f of x, the limit of f of x as x approaches 2, is it 1 or is it 3? Which do you choose? Doesn't exist. So in order for a limit to exist, the limit from the left and from the right must come to the same value. And in this case, we get a limit that doesn't exist because the left-hand limit and the right don't match up. Let's look now at a special function. It's called the greatest integer function. Just a new definition, just a new function to be familiar with. The greatest integer function, it looks like this. We've got an x in these special brackets, and we describe this as the largest integer that's less or equal to x. So greatest integer of 4 is clearly just 4, because 4 that's less or equal to 4. When we go to 4.8, the greatest integer of 4.8, the biggest integer that's less or equal to 4.8 would be 4. So another way to see this is that we're always rounding down. Pi is approximately 3.14, so rounding down 3. If we took the square root of 2, if we rounded down, we'd get a 1. Negative 1/2. If we rounded down, oh, you've got to be careful when you're looking at negatives. So look at this, just if you're thrown off by that negative. If we put that here, and we're going to round down, you see we're always rounding to the left. We're always rounding down. So that negative 1/2 would round to negative 1. Compare that to a 1/2. Integer of 1/2, round down, so that would be 0. At negatives, it might not be obvious without thinking through what that number line would look like, but that's called the greatest integer function. It's just a new definition for a new function that we'll be using. Might help you to look at a graph for the greatest integer function. So if that graph helps you, the graph is also in your textbook, or you can pause this video to look at it, but be familiar with that greatest integer function. We'll talk a little bit more about the greatest integer. Two more theorems to look at. First, if f of x is always less than g of x, then we can say that the limit of f of x is always less than the limit of g of x as x approaches the same value. So as the limit of f of x as x approaches a, or equal to the limit of g of x as x approaches a, if f of x is always less than g of x. And then from that we can develop the squeeze theorem. I want to go into just a little bit more detail of the squeeze theorem, but take a good look at it. If you need to, pause the video but what we have is a situation where this g of x function is sandwiched in between the f function and the h function. And it could be equal to f or h, but it's always in between the two or equal to them. So here's an example. Here's what that would look like. If h is the blue and f is the yellow, notice that g function, I'll highlight it in red, is sandwiched in between f and h, on at least on this interval. If you look to the left, you can see that red g function may cross over and become greater than h, but that's outside the region that we're looking at. So we're just going to look at for this region of the graph, for this part of the graph. So that g is sandwiched in between. What we have from that is that if the limit of h as x approaches a is equal to L, and the limit of f as x approaches a is also L, so we've got that the limits of the blue and yellow functions are approaching the same value, then what follows, what the theorem tells us, is that the limit of g must also equal L. We'll work a little bit more with the squeeze theorem in class, but make sure you're somewhat familiar with it before you get to class. Thanks for making. If you have any questions about the material that was covered, please make a note of it and bring those questions to class.